This problem asks us to design a common source MOSFET amplifier for a gain of -10 and using all of these conditions. So we have our LT-SPICE circuit with a 1.8 volt DC source, a single capacitor, a number of resistors, and an N-type MOSFET. Now our MOSFET needs to have the parameters in the problem, so we're going to rename it, and then we're going to use a SPICE directive to specify the parameters Kp, VTO, and lambda. So we use my NMOS, Kp is this number times this number, so that's 0.011. VTO is the same as VTH. LT-SPICE uses VTO, the turn-on voltage, and we often use VTH, the threshold voltage. Those are the same variable. So 0.4, and then lambda is also given to us, is 0.1. So we have our LT-SPICE setup, and we will begin our solution by deriving the gain equation from the small signal model, because we want a gain of -10. So we'll begin with our AC source, Vin, and then for the small signal model, we turn off our DC sources by shorting our 1.8 volt source to ground. So that makes our 1 go to ground, and our 2 also goes to ground. And then we'll draw our MOSFET. This is VGS, and we have our dependent current source, which is GM VGS, and R0 is also part of the MOSFET, and then we also have RD on this side of the MOSFET. This is V out here. So for the gain equation, we want V out over V in, so we'll begin with V out equals I times R, and R, so V out is the drop across, or the V out goes from across RD and R0 to get to ground. So we can do RD and R0 in parallel. And the current, we can draw the circle here where the current goes down to ground on the left side, which means that it goes up across the parallel combination of RD and R0. So we have a negative GM VGS for our current from V out to ground. VGS equals V in, because on this side of the equation there is no resistor between V in and VGS, so those are equal. And then for GM we have an equation, it's the square root of 2ID times Kp. That's a good equation to know. We'll plug that in for GM, and then we can write our gain equation is V out over V in equals A, that's gain. Gain is 10, -10, equals negative GM, which we know is 2ID, square root of 2ID Kp, multiplied by RD in parallel with R0. Now R0 is typically much larger than RD, so we're going to make that assumption and neglect R0, and then we'll come back and double check that that assumption is valid when we get to the end of our analysis. So we now have one equation and two unknowns, because we know Kp is 0.011. We solved that at the very beginning. So our unknowns are ID and Kp. We need another equation in order to solve for ID, not ID and Kp, sorry, they're ID and RD. And we need another equation in order to solve for ID and RD. So we're going to use the DC bias point equation. So we want our bias point, our DC bias point, to be between 1.8 volts and 0 volts, because those are our voltage rails. So we're going to choose 0.9 because that's right in the middle. So we want 0.9 volts to drop across RD so that we have 0.9 volts at V out 1, and the rest of that voltage will drop across the MOSFET. So now we have two equations and two unknowns. We can solve for ID and RD. So ID is going to be 178 microamps, and RD equals 5K. So we can plug in 5K for RD. And then we're going to choose R1 and then sweep R2 in order to get the current across RD to be 178 microamps. So in order to choose a value for R1, we want to make sure that our corner frequency is lower than 1K because the frequency of the signal that we're inputting into our circuit is 1 kilohertz. And R1 and R2 affect the corner frequency. So corner frequency equation is 1 over 2 pi R Thevenin times C, and C is 1 microfarad, and we want this corner frequency to be greater than 1 kilohertz. So we can solve that for R Thevenin, and we get that R Thevenin has to be greater than 159. R Thevenin is the equivalent resistance looking into the circuit, or looking both ways from the capacitor in the circuit. So looking toward the sine source, we don't have any resistance there, so we don't have anything on that side of the capacitor. On the other side of the capacitor, we have R1 in parallel with R2 in parallel with the input into the MOSFET. And if we look at our handy-dandy MOSFET equation sheet, the input into the MOSFET, input resistance into the MOSFET is infinite, approximately infinite. So we don't need to, we can neglect that in our equation. We don't need to include that in our parallel combination. So that's R Thevenin is R1 in parallel with R2, in parallel with infinity. So we're going to leave R1 at 1K, and we're going to sweep R2 to get the current that we want, and then we're going to double check that our parallel combination is greater than 159, so that we're not attenuating our 1 kilohertz frequency input, because that would give us a gain of less than 10, even though we had otherwise designed the circuit correctly. So we're going to use another SPICE directive, dot step param, to sweep R2. And so that's dot step param R. So we used R up here. And we'll sweep from 100 to 1K. And increments of 100. We're going to do a DC op point. And we're looking for a current of 178. So it's going to be somewhere between 450 and 500. So we'll zoom in on our sweep. And we still want 178. We're going to be about 466. And that's about 178. So now we'll switch over to our transient analysis. Before we do that, we want to double check our parallel combination. So when we combine 1K in parallel with 466, we get 318. And that's greater than 159, so we're good to go there. So we shouldn't be attenuating our signal based on corner frequency. So now we can check that our gain is what we designed it to be. And we have a gain of about 8.5. So we wanted a gain of 10. So we're just going to increase RD a little bit, since that has the most direct effect on the gain, from 5K to 6K. And that gives us a gain of about 10. So we want to check a couple of things before we call this our solution, for sure. So we want to make sure that we're in active. You would think that if we design a circuit and it gives us the gain that we want in LT Spice, that we are inactive. But it is possible for LT Spice to give us a solution that looks right even though we're not. fully in the active regime. So we want to make sure that we are. So watch out for that. So in order to be an active, we need VDS to be greater than VGS minus VTH. So VDS, we can use our DC bias point there from the third voltage from across the green. The source is about 749 millivolts. And in order to find VGS minus VTH, we're going to use our ID equation. So this is another good equation to know. ID equals 1/2 Kp times VGS minus VTH squared times 1 plus lambda times VDS. VDS is 749 millivolts, lambda is 0.1, so 0.1 times 0.7 is much less than 1. So this is about 1, and multiplying the whole equation by about 1 is not really going to change it, so we can neglect that. So we can solve this for VGS minus VTH. That equals the square root of 2ID over Kp. And that equals 178 millivolts. So our active condition says that 178 millivolts needs to be less than 749 millivolts, which it is. So we are in active. Last thing that we want to check is this assumption that we made up here. We want to make sure that RD is much smaller than R naught. So we have an equation for R naught. It's 1 over lambda ID. That's a good equation to know. Lambda is 0.1. ID, we can use our actual ID from our final equation, from our final circuit. It's about 175 microamps. And so when we solve that, we get that R naught is 57K. Now our assumption was that 57K is much larger than RD. RD in our final circuit is 6K. And we defined much larger as being 10 times larger. So 10 times larger than 6K is 60K, which is a little larger than our actual R naught. So this assumption is almost satisfied, but not quite. So I went back and checked how this gain equation would have been different if we had included R naught and not neglected it, since this assumption isn't quite valid. And if we had included R naught in this circuit, we would have gotten that RD should have been 6K and ID should have been 0.15 milliamps. Now 6K is what we actually used in our final RD. So in this situation, we adjusted for the fact that our assumption was not quite valid by just adjusting our final circuit values in LT-Spice. Now that can work if our assumptions are close. If our assumptions ended up being not very close, we may end up with a circuit where we have trouble figuring out what the problem is and why the circuit doesn't work. So checking your assumptions is a really good place to start if you do all the math and then you end up with a circuit that doesn't work. In this case, it was close enough that we were able to adjust in LT-Spice. That's a good thing to be aware of. So we've now checked all of our conditions. We have the gain of 10 that we were looking for. And this is our solution.